Sequences and series. The goal of this whole series section is to approximate values of functions by approximating those functions as polynomials. Since a polynomial is a sum of terms of x with non-negative integer exponents, we can think of a polynomial as a sum of powers. In this way, a polynomial of degree n is Pn of x equals this. For example, a quadratic is P2 of x equals this. This summation is also called a series that adds up an ordered list of terms, and this ordered list is called a sequence. A lot of ideas of limits for functions can be analogously applied to sequences, since sequences can be thought of as a function that only take positive integer values as arguments. But be careful. The functions are the gray curves, while the sequences are black dots. On the left, the function 1 over x and the sequence 1 over n have the same limit of 0 as they go off to infinity. On the right, the function cosine 2 pi x does not have a limit at infinity due to oscillations, but the sequence cosine 2 pi n has a limit of 1. Sequence a1, a2, a3, and so on. Above, an infinite sequence is an ordered list of terms, and the entire sequence is denoted by a1, a2, and so on, equals an, equals this, where n element of positive integers. Note that a set is a collection of objects where order is not important. A sequence an has the limit L in R, and we write limit n to infinity an equals L, or an to L as n to infinity. If limit n to infinity an exists, we say the sequence converges or is convergent. Otherwise, we say the sequence diverges or is divergent. We can diverge by going to positive or negative infinity, by oscillating, etc. Series. N equals 1 to infinity an equals a1 plus a2 plus a3 plus and so on. Above, an infinite series is the sum of terms of an infinite sequence. The nth partial sum of a series is Sn equals this. If the sequence of partial sums Sn converges, and limit n to infinity Sn equals S exists as a real number, then the series an converges. Otherwise, if sequence Sn diverges, then series an diverges. When series an equals S, the number S is called the sum of the series. For convergent series an and bn, these are also convergent. This and that. A convergent and convergent series is a convergent series. A convergent and divergent series is divergent series. But divergent and divergent series is inconclusive. Consider these becoming divergent, but these becoming convergent. If this converges, then the full series here also converges. A finite number of terms does not affect the convergence or divergence of an infinite series. The squeeze theorem. If this for that and these, then limit n to infinity bn equals L. The monotone convergence theorem. Every bounded monotonic sequence is convergent. A sequence an is bounded if it is bounded above, where an less than or equal to big M, and bounded below, where m less than or equal to an, for all n greater than or equal to 1. Thus, an greater than or equal to m less than or equal to big M. A sequence is monotonic if it is either increasing, if an less than an plus 1, or decreasing, if an greater than an plus 1, for all n greater than or equal to 1. In particular, a sequence that is increasing and bounded above converges, and a sequence that is decreasing and bounded below converges, similar to an asymptote for a function. Telescoping series. A telescoping series has a finite number of terms after cancellation. For example, using partial fractions, we have this. The partial sums eventually yields only two terms, and so s equals limit n to infinity Sn equals 1. Here is a flowchart. Form of a series is more important than a flowchart. Although a flowchart helps organize the tests, the form of a series is the deciding factor in picking which convergence divergence test to use. Often, you have to manipulate a series into an easier form, or compare it to a series with an easier form. Thus, although the original components of a series might hint at a particular test, you might actually pick a different test after you've done some work. Additionally, even if you found a test that works, there could be other tests that are just as valid. Here is a fact sheet. The divergence test. If limit n to infinity an does not equal 0 or does not exist, then series an diverges. Equivalently, if the series an converges, then limit n to infinity an equals 0. The contrapositive of the implication, if P then Q, is if not Q, then not P. For example, if you have a cat, then you have a pet, becomes if you don't have a pet, then you don't have a cat. The divergence test is inconclusive if limit n to infinity an equals 0. That is, we cannot say anything about the convergence or divergence of the series. Note the problem with saying, if you don't have a cat, then you don't have a pet. One could have a dog as a pet. The geometric series test. For series n equals 0 to infinity a to the power n, if absolute value r less than 1, then it converges, and its sum is a over 1 minus r. If absolute value r greater than or equal to 1, then it diverges. The partial sum is this. For a divergent case for both the divergence test and the geometric series test, consider series 2 to the power n, where we're always adding something positive and increasing. We have the following. For an inconclusive case for the divergence test and a convergent case of the geometric series test, consider series 1 over 2 to the power n equaling this. We have the following. Geometric series examples. For the sequences r to the power n, where r is a common ratio, we have the following. In summary, limit n to infinity r to the power n equals 0 if r greater than -1 less than 1, 1 if r equal to 1, divergent otherwise. Note how different tests tell different things about sequences or a series. And we have the following. The integral test. If series AN has an analogous function that is continuous, positive, and decreasing, then the series converges if integral 1 to infinity f of x dx converges, and this series diverges if the integral diverges. Generally, series does not equal integral. For us, we'll use the integral test to prove the upcoming p-series test rather than integrating analogous functions. An inconclusive case of the divergence test is the harmonic series, series 1 over n, since limit n to infinity an equals 0. But now we can prove that it diverges based upon the integral test. Its analogous function is continuous, positive, and decreasing, and its improper integral diverges. Here. Remainder estimate for the integral test. Consider an infinite series S that equals its partial sum, Sn, and remainder, Rn. We have the following. Suppose f of k equals ak, where f is a continuous positive decreasing function for x greater than or equal to n, and series an is convergent. Then we have the following. Here are some pictures. A series ending at n has a remainder Rn starting at n plus 1. Note that the area of Rn equals this is between these improper integrals. The p-series test. For a p-series, 1 over n to the power p, if p greater than 1, the series converges. If p less than or equal to 1, then the series diverges. If p equals 1, then it's the harmonic series. The following examples will be useful for the upcoming comparison tests. We have the following. The direct comparison test. For positive series an and bn, if an less than or equal to bn and series bn converges, then an converges. If bn less than or equal to an and series bn diverges, then series an diverges. Usually compare with p-series or geometric series. For a convergent case of the direct comparison test, consider a series that yields terms that are smaller than the terms of a convergent series. We have the following. For a divergent case of the direct comparison test, consider a series that yields terms that are larger than the terms of a divergent series. And we have the following. The limit comparison test. For positive series an and bn, if limit n to infinity an over bn is a positive real number, then either both series converge or both series diverge. Useful for rational functions or radicals, and usually compare with p-series or geometric series. Used for when the direct comparison test results in the wrong inequality, when we're smaller than divergent series or larger than convergent series. Similar to finding asymptotes of rational functions. For a convergent or divergent case of the limit comparison test, consider a series that yields terms that eventually behave like positive constant multiples of the terms of a convergent or divergent series. This series is convergent like that series, and we have the following. This series is divergent like that series, and we have the following. The results are inconclusive when the limits equal infinity or zero because they could be found from various combinations of convergent and divergent series. Divergent convergence are these, convergent convergence are these, divergent divergence are these. And we have the following. The alternating series test. For a series an that equals -1 to the power of n minus 1 bn, where bn equals absolute value an, if bn plus 1 less than or equal to bn, and limit n to infinity bn equals 0, then the series will converge. A convergent case of the alternating series test is the alternating harmonic series. Here. Note how this and that. Another example is this. Note how this and that. A series an is absolutely convergent if series absolute value an is convergent. For example, this is absolutely convergent since both this converges and that converges. A series an is called conditionally convergent if it is convergent but not absolutely convergent. That is, if series an converges, but series absolute value an diverges. For example, this is conditionally convergent, since this converges, but that diverges. If a series an is absolutely convergent, then it is also convergent. Thus, you can prove that series an converges if you can prove that series absolute value an converges. But if series absolute value an diverges, then it is inconclusive concerning this convergence or divergence of series an. For example, this diverges and that converges, while this diverges and that diverges. Alternating series estimation theorem. If this, where bn greater than 0, is the sum of an alternating series that has bn plus 1 less than or equal to bn and limit n to infinity bn equals 0, then we have the following. In words, the size of the error is at most the absolute value of the first neglected term. This is because S lies between any two consecutive partial sums Sn and Sn plus 1. We'll see examples of this when we do Taylor series approximations. The ratio test. For a series an, if this less than 1, then it is absolutely convergent. If this greater than 1 or infinity, then it is divergent. If this equals 1, the ratio test is inconclusive. Used for fractions where numerator and denominator are different type of multiplication, products, factorials, nth powers, etc. The growth of functions can be helpful from L'Hopital's rule. Ln n grows slower than n to the power p, goes slower than a to the power n, goes slower than n factorial, goes slower than n to the power n. Consider the ratio test to these geometric series. We have this, the series converges. We have that, the series diverges. With geometric series, the ratios between consecutive terms are constant, and so the limits don't do anything. For other series, the ratios between consecutive terms wouldn't be constant, and so the limits do something. For convergent and divergent cases, consider series that yield terms that eventually behave like a convergent or divergent geometric series. This is absolutely convergent, like that, since we have this. This is divergent like that, since we have this. For inconclusive cases, consider how both the divergent, series 1 over n, and the convergent, series 1 over n squared, have this, and that. In general, the ratio test is always inconclusive for rational functions. The root test. For a series an, if this less than 1, then it is absolutely convergent. If this greater than 1 or infinity, then it is divergent. If this equals 1, the root test is inconclusive. Useful for nth powers. Consider the root test to these geometric series. Here, the series converges. There, the series diverges. With geometric series, the roots are constant, and so the limits don't do anything. For other series, the roots wouldn't be constant, and so the limits do something. For convergent and divergent cases, consider series that yields terms that eventually behave like a convergent or divergent geometric series. This is absolutely convergent like that, since we have the following. This is divergent like that, since we have the following. For inconclusive cases of the root test, consider both the divergent series 1 over n and the convergent series 1 over n squared have this equals 1. We have this, and we have that. In general, the root test is always inconclusive for rational functions.